Hey everyone, welcome to the VLSI Design and Verification Professional Training Program by Logixels Technologies. In this session, you will understand the semiconductor industry, VLSI ecosystem, and the roadmap to become industry-ready design and verification engineer. Let's begin your journey into the world of chip design. And if you want to enter into the exciting industry, this training series will help you to build the right foundation. Companies like Nvidia, AMD, Qualcomm, Intel, and all the product companies hire thousands of VLSI engineers every year. Many engineering students know software roles, but very few understand how chips are designed and verified. So, let us welcome you all once again to your journey into the world of chip design and verification. You guys, I think no, India has started a major journey to become global semiconductor powerhouse through the India Semiconductor Mission started in 2021 with a strong government support and many investments worth around 70,000 crore. The new chip manufacturing and packaging facilities are being set up. This growth is expected to create thousands of opportunities for future VLSI engineers. So we need to understand which are all the product companies in VLSI. They are working on design, manufacturing, and also equipment tools, and they will be providing EDA tools, and they are working on different aspects of VLSI. See, there are some government companies also work on VLSI design and fabrication, we can say, DRDO and other well-known companies, even some IITs has a research unit on semiconductor. And there are many other companies also here, only two, three as mentioned. So if you come to design, major industry design contributors are Intel, Qualcomm, Nvidia, Analog Devices, Texas Instruments, NXP. All these are contributing for the design actually. They are working on high-end computing devices and they will bring to the market quickly, we can say. Why? Because they have that infrastructure. The design is very important. And after the design is done in any company, they may give it to the service companies for verification. They may have their own unit. In design verification, there are more opportunities. Why? Because if the design is going to be taken some 6 months of time, verification takes some 1.5 year of time to complete. So design verification has more advantages here, and it is a more domain requires more manpower as well. So these are the companies work on design, and some of the companies here I have listed which work on manufacturing things, and also you might have seen Synopsys, ARM, Mentor, Cadence, even Siemens. All these are EDA providers, EDA tool providers. You might have seen Cadence tool, Cadence Virtuoso, even Xilinx, AMD Vivado, ARM processors, controllers, and even ARM has some tools also. Synopsys VCS simulator, Mentor graphics, all these are EDA tools which will be supporting designs. Okay, these are some of the companies I listed here. So basically, what you need to understand is product company in VLSI is not only design or not only directly manufacture and sell it goods. Okay, so there are different categories in that again. We have IDMs. IDM means integrated device manufacturer. See, they have their R&D center. They will be doing the design, and they will be having their own fabs as well, and also back-end facilities, and also they sell their branded semiconductor products. Okay, the best example is Intel. If you see Intel, Samsung, TI, Micron, they will do end to end. They have their own ecosystem. So that will be called as integrated device manufacturers, IDM. These are very big companies. You can target these if you want to work in a exact product based project. Then there are foundries. You can see TSMC, Samsung Foundry, Global Foundries, UMC. These work on actually the manufacturing of silicon, what you call it as integrated circuit. So there are foundries. Then many companies are fabless manufacturers. Fabless means design and sell the semiconductor chips without owning the fabrication facility. They don't have their own fabrication unit. They will be dependent on others. Let's say they will give it to TSMC, they will give it to Samsung Foundry, Global Foundries, And many companies like Nvidia, Qualcomm, AMD, Broadcom, they do their design and they do all the requirements of the IC, and they will give it to TSMC and other foundries for manufacturing. Then we have outsourced semiconductor assembly test units as well. These provide assembly, packaging. If you see, once the silicon is out from the fabrication, there are many things to be done upon that to provide it to an user. So assembly is also very important aspect here that will be done by some of the companies. Then IP providers are there. You might have heard about ARM, Synopsys, Cadence. These provide EDA tools, and also they will provide verified IPs, intellectual property blocks. So you can use these IPs directly in your design since they have already verified. So these are the different product company categories we have in system semiconductor. Okay, it means in VLSI. So product company doesn't mean it will design their own product, it will manufacture its own product, not like that. There are different types of even product companies. Okay, then you can see it clearly here. IDM means they design, manufacture, test, sell their own products. That's why you see Intel products, you see Samsung products, you see TI products, NXP products, Infineon, ST, Micron. All these are IDMs. Foundry means basically TSMC is a very big foundry. Nowadays, we are trying to have one foundry at least in India, right? So the other companies are global foundries and all. Fabless companies are more actually. Nvidia, Qualcomm, AMD, all these guys has their potential in designing the things. They bring up the new technology and they design, but they will not manufacture their own. Means they will not have a fabrication unit. So they are fabless. And also I told many others. And also observe there are many service companies. So if you name any service company which is there years back with software services, now they are into VLSI. Remember this. Wipro, HCL, TCS. Wipro, HCL, L&T are from long back. They are servicing for VLSI products. But if you see TCS and if you see Tech Mahindra, if you see Capgemini, and any big service company, software service company, if you name, even Quest Global, UST Global, Infochips, Infosys, even Infosys acquired some small VLSI company and they started semiconductor. Even Google, Apple, Amazon, everyone has semiconductor unit now. So in if you name any company that has a semiconductor unit nowadays. So that is how VLSI is growing, and you will be getting more opportunities nowadays. Why? Because the globally the usage of electronics increasing. Every automobile will be having multiple ICs inside. Many automations are going to happen over there, and even AI, what we are talking about today, will be powered by high-end processors as well as ICs only. Okay, whatever the AI model you are going to have, that should be in a high-end processor which supports computing, right? So here in our training program, we are heading to design verification. Remember, so in VLSI, basically, if you take an ASIC design, there are two clear-cut categories we can make. One is front end, another one is back end. Similarly, as we see in software, we will be having a front end design and back end design engineer. UI design engineer will be called as front end engineer, and Python and back end support will be called as back end. Similarly, here also in ASIC design, we have front end and back end. Front end means what? I will tell you very simple words. I will tell you in very clear cut simple words. You guys have studied Verilog in your academics. You guys have studied VHDL. You might have studied C, C programming, Python, Java, all programming languages. So in VLSI, the digital design what we are going to code, so that is Verilog and VHDL, comes in front end. See, at the second stage of front end design, we have Verilog here. Okay, this is what we call it as front end. If you write a code for any design using Verilog or VHDL or any other supported language, let's say system Verilog also sometimes, then it is front end. You are working in front end domain. What exactly back end mean? If you want an IC, then IC has many sub blocks inside. You might have seen different layouts in your academics. So that has many blocks like this. It is arranged in such a way that every component is to communicate properly. It will be having power rails, it will be having all the bus lines, everything will be placed clearly in a chip. So where actually we need to place which component and how actually the routing between them, how to manage the clocks we have, and all those things will be in comes in backend. You might have studied layout, so that is backend. Physical design (PD), what we say, that is backend. The front end engineer is going to write a Verilog code, and the next level of writing Verilog code is verification. Means whatever the code you have written in Verilog, we need to verify whether that works properly as per the requirement. So that is functional verification. So this is where we call it as DV, Design Verification Engineer. So here we call it as HDL, Hardware Descriptive Language Verilog or VHDL we are going to use. Okay. So then in front end you will be writing a Verilog code, and also you will be writing a test bench to verify the functionality of the design. So simply, if you are a student, if you are a early graduate, you can understand it like writing some code to satisfy the functionality and verify that functionality is your front end. So then the next steps of your verification will be, you will be synthesizing the design. Once you synthesize, you will be getting a kind of hardware what you are going to get in, what is the kind of hardware I am going to get for the particular code I have written. Then after the synthesis also there will be a verification. Functional equivalence with RTL can be ensured here. Then floor plan, placement, CTS, that is clock tree synthesis, your routing, sign off verification, then GDS file and tape out will happen. So this is a brief flow of how an IC life cycle will be. Then if you look at design verification flow, I said design will happen here and the verification of functionality will happen immediately in the next stage. So now in our training, we are concentrating on this stage, third stage. Okay. So to enter into third stage, you may get a question that, do I need this second stage? Do you need this second stage understanding if you want to be in third stage of IC lifecycle? Yes. If you want to work as a verification engineer, at least you know how actually the design will be, what exactly the RTL code mean, how that RTL code is written, what are all the functionalities like that. So for a design verification engineer role, you need Verilog first. You need to understand the design. Then only you can verify that by writing the test bench. Okay. So the thing is, in a verification, let's assume like a design is ready. You have a Verilog code with you. Okay, let's assume it like a .v file. This .v file will be having set of lines to satisfy some functionality. Okay, so you need to understand the specification first. What exactly the design requirement is, what exactly the functionality they have written in RTL level. That is your very first thing in a verification flow. If you want to be a verification engineer, remember, you have to understand the design properly. You have to have a clear cut idea on how the design is. Okay, at least not in a deeper level, at least functionality level, you need to understand how exactly the design is written. What are all the functionalities they have covered at least. So then you need to plan your verification. We can't simply write a test bench. You might have heard about a Verilog test bench. You are going to write test bench file. That test bench file is a single test bench file you will be writing for any Verilog design you have written. So you can't write a test bench file directly like that. If it is a very simple design, it is easy to port that into a test bench. But you need to plan the verification activity by keeping some strategies that I will be verifying this design in this way. That is verification plan. In industry, this is the flow. Okay, remember this. Even if you are attending any interviews tomorrow on design verification, if they ask, do you know design verification flow? Yes, you need to start with specification understanding. Here only you need to say design understanding. Then you need to say, I will plan the verification. Then I will write the test bench. See, please don't directly tell I will be working on the test bench, that is my first task. No, you need to understand the specification, then you will be writing a verification document. See, in DV there might be a team of some 10 members. Okay, one senior people member will be there, he will be leading you, and then a higher level architect might be there. So usually they will be writing this document, verification plan document. Specification document is also a document you are going to get from the design side. Verification planning is also a document they are going to prepare. I am talking about document means how you are going to prepare your project report at the end of your semesters in your academics, like that. They will be preparing a document. You will be provided with this document to understand the things. Okay, so it has verification plan. Then comes the test bench development. Here exactly the code of Verilog test bench exists. What you are going to write the test bench in Verilog, right? This is where you will be writing that. But in industry nowadays, we will be having complex designs. Does that Verilog test bench enough? Verilog is enough for verification of the functionality? No. This Verilog is sufficient for design. To write a test bench, we need system Verilog and we need UVM. Remember, if you want to be a design verification engineer, you need to learn these two things in a proper manner. If you know Verilog, you can be a design engineer. But there are other deeper concepts in design as well. You need to understand that if you want to be a design engineer. If you want to be a verification engineer, if you want to work on the test bench side, then you need to know Verilog, system Verilog, and UVM. Let's understand what extra we are going to get in system Verilog, why we need to learn system Verilog for verification, why Verilog is not so sufficient, why can't we write a test bench in Verilog? It looks simple. We have already studied this in our academics. No, that will not work. For verification, you need system Verilog. System Verilog supports scope features. So using class, we will be writing the test bench in system Verilog. And we need UVM as well. UVM in the sense universal verification methodology. Means whatever the system Verilog constructs are or concepts are, the same system Verilog concept based standard methodology is set by industries, that is UVM, universal verification methodology. That methodology need to be used while setting the test bench. In UVM, the advantage is that we have many base classes. Base classes means what the minimum test bench requirement is, that is already written. It is present already in the library. You need to pick this class and you need to write extra things over there. You need to pick this class, you need to write some extra things over there. You need to pick the available class and you need to write the extra things. So writing the test bench in UVM is simpler than system Verilog. Okay, but UVM based on what? Which language? Can anyone tell me? UVM is based on what? Is it UVM a other language we need to understand? We need to learn? If anyone know about UVM already, or you might have started learning system with learn, please tell me. Do you think UVM is a new language to learn? No. UVM is just a standard methodology we are going to write the test bench using system Verilog. Okay. So UVM make our things easy. Okay. So UVM will be used in test bench development. Remember this. Remember that. Then simulation and debugging. Obviously, once we write a test bench will be used to provide the stimulus to the DUT. We will be generating some data required for the DUT. So we will be simulating that, and if any bug present, we need to debug it. We need to detect it. Okay, detect and fix the design bugs is the functionality or the role of a design verification engineer. Design verification engineer's actual role is to find the bugs present in design, right? Find the flaw present in the design. If design is not meeting some specification, in the verification you need to find it. Every test case is passing means we are not writing the test bench correctly. We are not verifying the design correctly. That is how it is. Okay. If you are a verification engineer, you are working exactly on the functional verification. You need to find bugs. That is what your task is. And you need to report to the designer that, hey, there is a bug here, fix it. If there is no flaw in the design, if the design is so perfect at the design stage itself, then there is no scope for the verification engineer at all, right? So understand one more thing. Suppose, let us consider in a percentage. Suppose if an IC take, let's say, 2 years to complete its design, development, verification, and everything. What is the maximum time spent for verification? Can anyone guess? Verification takes 60 to 70% of the time. So 70% of your IC design and life cycle will be the time spent in verification. 70% of the time spent in verification, or at least 60% of the time spent in verification. So verification is so critical. It is so required. That's why if 3 design engineers are there, at least 6 to 7 verification engineers will be present in a team. You can check with your seniors if they are working in industry. So there is more demand for verification engineers even in entry level compared to design engineers. So even enter into the design verification role is bit easy compared to design, and this demands more manpower. Okay, why? Because we need to find the bugs present in the design. Okay, then does functional verification through simulation is sufficient to find the bug? No. Your simulation will not provide you 100% guarantee that your design is correct. You need to do coverage analysis. Coverage analysis mean what? How much of your design functionality is covered through your verification. Let's say I have 10 functionalities in my design. I have written a test bench. I have planned my verification. I have covered 9 functionalities. And one functionality is very simple, or it is a corner case. It never used by any there is no use case for that, but simply for um, some usage they have added it. We can neglect it? No. You need to cover it 100%. All the 10 functionalities to be covered. Suppose, let's say, I will tell you in another way. Suppose design has 100 lines of code. Your design will be having 100 lines of code. Suppose through your test bench, you have executed the design. Let's say 95 lines of your code executed, and some else part, some default lines, some declarations have never executed throughout the simulation. Then your verification covers 95% of your code. Who will cover another 5% of the code? At least once your design code has to be executed. Otherwise, these 5 lines are dummy, right? So your coverage should be 100%. Means you need to cover all the features, even small, minute design aspects in your verification. That's why it take much time. Okay, even a simple coverage analysis, once you complete all the test cases and simulation is done, 100% verification is done, but still it is taking time. Why? Because you need to cover everything in the design. That is coverage, functional coverage. This will give you the score. It will give you in terms of what is the line it is missing. Suppose if this line is missing, it will indicate this is missing, you are not at all covering this. You can waive off if it is not so important, or you need to write the test case for this if it is so covered, if it is need to be covered. So that is coverage analysis. It is just like, suppose if you are exploring Bangalore and there are, let's say, 50 areas in Bangalore, you have covered 40. Some 10 areas are very small areas. You might have not go there. So your coverage is only 90%. You missed some 10% of areas. It is just like that. Many people say, I know Bangalore fully, but they have not covered all the corner areas of Bangalore. Then they have covered only 80%, 70%, like that we will tell, right? In the same way, if design is having, let's say, 100 lines of code, if you have covered 99 and one is missing, your tool will identify that. There is a mechanism to do the coverage analysis. So that provides you a clear-cut idea of verification. Then we do regression. Regression testing also will be done. In regression testing, there are some automated test runs we will be doing continuously. It may fail in some rare cases. Okay, it may fail in very rare cases, conditions. So that will be covered in regression. So these are the different aspects of verification. Verification is not only writing a system Verilog or UVM code. Just look at the waveform. If everything is works fine, done. No, there is coverage, there is regression part. Until you sign off the verification, you have many things to check. All the test cases should pass for all the different values. Anyone of you heard about randomization, randomized stimulus, randomized data? 2:1 multiplexer mean it will be having two inputs. Okay, it will be having two input lines and it will be having one output line. If the two input lines are a single bit inputs, there are four possible inputs: 0, 0, 0, 1, 1, 0, 1, 1, right? For a 2:1 multiplexer verification, we need to provide those four input values. And another input bit will be there, that is select line. That can be 0 or 1, like that. I'm talking about only 2:1 mux. A simple 2:1 mux will be having four inputs. If you are trying to give manually, you need to provide four lines of code. A should be 0, B should be 0, A should be 1, B should be 0, like that. Four combinations, right? Suppose if it is a 4:1 mux, can anyone tell me how many different combination of inputs we need to provide for a 4:1 mux? There are four inputs now, 16, right? 0, 0, 0, 0 to 1, 1, 1, 1 you need to provide. Suppose if it is a 8:1 mux, how many set of inputs you need to provide? Suppose if it is an 8:1 mux, 8 inputs, right? So nowadays, the systems what you are using today, the laptops, computers, and even your mobile phones are operating with 32-bit and 64-bit, right? So for single input, let's say 4:1 multiplexer, input A will be operating with 32 bits, 64 bits. In that case, manually, is it possible to cover all those cases manually? No, there is some random way to generate them. That's why randomization is required. You need to provide the data randomly to your design and you need to verify that. Suppose let's take a very simple example. You will buy a calculator. You will go and buy a calculator. You will just check 1 plus 2 is equal to 3. Oh, it is coming correct. You will hardly check 2 into 3 is equal to 6. Yeah, it is correct. If you are an enthusiast, you may check some division as well. 10 by 5 is 2. No one will check fractions. No one will check integrations. No one will check complex functionalities. Why we will not check all those means we assume that it is already verified for all the cases. It is already validated and it is come to the market. Correct? But you might have heard about Intel's Pentium 4 bug. There is a bug happened in Intel Pentium 4. Okay, while calculating the floating point divisions, if you search for FDIV bug, you will come to know floating point unit. There is a bug, so that caused a huge loss to Intel because of a simple or a very small negligence by validation or verification engineers. So it is providing wrong results for I think for fourth or fifth decimal point. Other than giving 7, it is giving 8, something like that. So usually we will not identify all those kind of errors when we are doing some small calculations. Mathematicians or scientists and accountants, so they work on very minute things. For them, it is very important. So one scientist identify that bug and report to Intel. Initially, Intel rejected it. Rejected in the sense neglected it. No one will be affected from this. We can't take much risk on that, like that. They given some reasons. Then they have replaced each and every product they have sold. Okay, that is the power of verification. That is what happens if you neglect a small bug inside your design. There are many other things happened already in industry. You might have, you can search. You will be not allowed to give the design to the next stage for synthesis and further things until your design is 100% perfect. Okay, that is why DV role is so important. DV role will be having many opportunities if you compare to other VLSI roles. So let's move forward. This is what the design verification flow is. We start with verification plan, end with verification sign off. In between, we will be writing the test bench, test cases, simulation, debug, coverage, regression. Okay, you need to remember these things. Then physical design flow. Let us not much go deeper on this. Floor plan placement, clock tree synthesis, routing, and physical verification sign off is the process flow here in PD. Then I will give you the clear-cut roadmap here if you want to be a VLSI design engineer. Remember, I said there are two aspects. One is you can be a design engineer, you can be a verification engineer. Okay. Design engineer mean he will be writing the design code. Means let's say he will spend much time on writing Verilog. Okay, Verilog module, right? A design engineer will be uh, well versed with the design, digital design. Then he will be knowing Verilog perfectly. Then you need to know Verilog in detail. Then system Verilog may be required in design stage. That is not so important. System Verilog will be predominantly used for verification actually. Okay. Sometimes some designs will also be written in system Verilog. Okay. So Verilog is so important. System Verilog for design is not so much useful. You can study only design aspects using system Verilog. Okay, no need of understanding of class and all for a design engineer role. But the very important thing here is lint and CDC. You need to understand this. This is very important. Linting and CDC and RDC. Nowadays, we will be having many subsystems inside an SOC. Okay, they are operating with different clocks. If you are going from one domain, one block of the system to other system, this might be working with some other frequency, this might be working with some other frequency. So when we are sending the data from one to the next block, we are crossing the clock boundary. It is just like we are traveling from, let's say, Karnataka border to, let's say, Chennai border. Sorry, the Tamil Nadu border. We are crossing it. It means the frequency of Karnataka or the language here is different. If you go to Tamil Nadu, the language is different, right? And they speak in different frequency. Here, Karnataka people speak in different frequency. Let's assume simple way. So you need properly. You need to carry your language features or communication skills to the destination. Then only you can communicate effectively, right? So that is your CDC mean, clock domain crossing mean. If you are crossing a clock domain to the other clock domain, the frequency changes. You need to take care of the data which is traveling from one block to other block. So if you want to be a design engineer, please go with Verilog, then lint CDC RDC understanding. Okay. Then comes AMBA protocols. Protocols is very important. You need to start with AMBA protocols. So bus protocols are there: APB, AHB, AXI, CHI, all those. So you need to start with APB at least to get into any role in VLSI. That is also required for design engineer role. Then professional development skills. You need to understand system level things. And also, if you want to be a FPGA engineer, you can be where FPGAs will be used for design and development and prototyping as well. Okay. So in designer role, you have different roles again. You can be a ASIC design engineer, you can be a SOC design engineer, you can be a FPGA design engineer, you can be a IP design engineer, like that. Okay. So this is for design engineers. Then comes design verification engineer role. Design verification engineer role demands, as I said already, it demands System Verilog UVM. Okay, Verilog SDL is mandatory for any role you go. Digital design is also mandatory for any role you go. But as I told in the previous slide, a designer role requires CDC RDC. Similarly, a verification engineer role demands you to know System Verilog and UVM. Okay, and protocols. At least you should know 2 to 3 protocols, and you need to work on 2 to 3 protocols to know about how system level works before heading into interview. Then only you can clear the interview easily. So this is for design verification engineer. Okay, so remember, design verification is not only writing the test bench, also coverage, assertion, and regression, coverage analysis. After coverage analysis, again going back to the test bench and writing the test cases, everything includes inside. Okay, and one more thing I can tell you clearly, entering into design verification role is bit easier compared to any other roles in VLSI. Okay, that is an advantage you will get if you choose DV role. If you want to be a design engineer, you will get very less opportunities, and in DV role you will be getting more opportunities in industry. Then in this 3 months of training, we will be using a EDA playground which is available in online. Okay, anyone can use it if you have an account. Okay, if you want to be a VLSI engineer, at least in design field or in verification field, if you don't know EDA playground, please spend some time today, create an account in EDA playground, start writing the code. You can write a simple Verilog code here. You can observe here I have written a simple 2:1 mux. Okay, and we have written a test bench for 2:1 mux here, right? It is very simple to use. Here you can see the project link, project path. Once you saved it, it will be created like this. You can also share it to anyone. So it is easy to handle the things. You can write a design code at the right side. This is your design area. Okay, and this is your test bench area. You can write a test bench. And you can select multiple languages here. You can select UVM if you want here, and there are multiple tools available also here. Okay, whatever the tools you are going to get in industry, let's say Altec Rivera Pro, Questa Sim, Cadence Xcelium, and Synopsys VCS, all those are available here only virtually. So the advantage of EDA playground is that you can learn uh, uh, programming or coding. You can come here and simulate it directly. This gives you the result even in the log format if you had some print statements like this, and also it will show you the waveform. Okay, I will show you. Yeah, this is the waveform. This kind of waveform analysis also you can learn in EDA playground itself. We will be using this during our each and every sessions, just to quickly go through the examples and to understand what exactly going on in that particular code. Okay, so remember, there is a myth, and there is one thing everyone will demand for is tool. Tool knowledge is required only when you have a knowledge of coding. Means if you have a verification knowledge, if you know system Verilog test bench, if you know UVM test bench, if you know test bench writing, then tool matters. If you want to learn system Verilog, UVM, this EDA playground is more than sufficient. Okay, without any tool, physical tool in your system, you can have tools here only, and you can execute the things. You can learn how actually a VCS simulator will give the result by looking at the log here. Okay, this log. So in EDA playground, you will be getting at least some 6-7 tools used in industry. So that is an advantage of using EDA playground. And also, as I said, then and there, suppose if I am explaining this 2:1 multiplexer, immediately you can write this code. If I give it to you, you can just put it there, and you can put this test bench code, and immediately you can run this. You will see results. It is easy for hands-on as well. So we will be using EDA playground in everyday session. So you can then and there you can simulate the things and see the things. And if you want to change something and try out, let's say wire declaration is explained, you need to change it to reg and try out. You can try out then and there. You can see the wave error over here. Then you can learn by looking at that error. Oh, if I change this wire to reg, this is what happens. So it is very easy. So in everyday sessions, we'll be using the CDA playground, and only for projects, we will be using the tool called QuestaSim. Every time we can't open QuestaSim, write some code, compile it, simulate it, it will take much time. Okay. EDA playground, if you have an internet connectivity, you can easily simulate the things. So please practice writing codes in EDA playground and simulate. Um, that is a very good exercise you can do in your learning duration. So we will be using QuestaSim as well for projects. Okay. Even today, this QuestaSim is used in many industries. This is provided by Mentor Graphics initially. Now it is acquired by Siemens. So this is now a Siemens enterprise. This Questa simulator provides all the advanced verification features. Okay, we can use it for doing some project, to get the waveform, to get the log, and to trace back the things, and also coverage. Everything can be done in Questa simulator. So Questa sim will be used in our 3 months, also in 6 months program. Okay. And now we need to understand some technical aspects. I talked about specification, RTL design, verification, synthesis, and finally chip, right? Where actually Verilog fits here? Where we'll be using Verilog? I told you already, we use in RTL design stage. Where we will be using system Verilog? In the simulation stage. Okay, remember this. This is your .v file. I can't write it properly here. .v. While doing the simulation, while verification, you will be using .sv files. System Verilog code comes into picture here. Remember, Verilog or System Verilog are not programming languages. We will be using Verilog to describe some hardware. If you write one line of code in Verilog, that turns up into a hardware when you do synthesis. So carefully, we need to write each and every code or each and every line in Verilog. It is not like any other programming language. So remember, it is a hardware descriptive language. It will be used for generating the hardware. We will get the hardware finally. So carefully, we need to write a simple code also in Verilog. We can't simply write 10 lines of code for a simple functionality. That 10 lines leads to 10 gates. You can make it in a single line, that may take some 3 gates, right? So writing Verilog code is not like any other programming language. You need to understand in a perspective of hardware design. And system Verilog code is used for test bench. I said you can play with your system Verilog test bench. You can write your own way. No one bothers you. No one will disturb you. Why? Because that is not going to be synthesized. Your Verilog code, what you are going to write, will be synthesized, and that becomes a hardware finally. This test bench code, what we are going to write, will be used only during the simulation. It will not go to synthesis, right? Your Verilog code or the design what you are going to write will be provided to the synthesis. So more effort required in design, that's why. Less effort required in verification. Why? Because the engineer effort required more in verification also. But the thing is, less rules, let's say, we can have flexibility, we can have more flexibility to write the code in system Verilog in verification for test bench. Okay. Then that's what I said. If you can't think in terms of logic gates and signals, you can't design digital hardware. You should not think like a condition is executing. We are checking if condition, then this statement is executing, not like that. You are checking a condition in real time. If it comes, how hardware should behave. Okay, you should think like which logic gate will be implemented if I use this construct. That is what your design is. That is what we call it as register transfer level. You will be having a register level hardware component, okay, that will be used to get some logical behavior, and I will be using different states if it is a sequential part, and we call it as logic, simple logic if it is a combinational part, and we will be having input and output signals to the design. So then we talked much about Verilog and the design, and no need of this. Okay. Now the thing is, let's say if you are designing a 2-bit counter, okay, 2-bit counter is your design. If you want to design this 2-bit counter, the thing is you need to understand, I need to generate a clock. You need to understand what frequency I need to generate a clock. You need to understand how the counter is resetting. You need to understand when actually counter roll back to 0, what is the maximum limit. All these are called as specifications. Okay. So after designing this counter, while verifying also, you need to follow these constraints. You need to generate your clock inside a test bench, which is supported by your design. You need to provide the reset according to the design, what they have written. It can be active high reset, it can be active low reset. You need to handle it carefully. And you need to verify this counter even starting from reset. The very first test case would be reset test. When reset, what is your counter behavior? What should be your output of a counter? It can be 0, or it can be a maximum value, or it should start with some mid value. That is what designer has designed and given in the specification. That need to be verified. Okay, that is your first test case. Second test case would be whether this counter is following the design aspect and it is counting for every clock edge. That is your second test case. The third test case would be whether this counter is reaching the final value properly by incrementing by 1. The fourth test case would be, suppose if I reset somewhere in between, whether it is rolling back to 0 or not. The fifth test case would be, suppose if I start this counter by without resetting the counter, what should be the state of this counter? Let's say for a simple counter, 2-bit counter, we are writing 5-6 test cases to verify that functionality. These are the test cases I am telling you so that you can understand. There are many other test cases involved to verify this counter. That is the role of a design verification engineer actually. Okay. So you can see here, this might be a simple design code for a counter. We have a clock, we have reset, and we have a 2-bit count. How this counter will behave? Always at positive edge of a clock, whenever the positive edge of clock comes, check the reset. If reset is 1, your counter should start with 0, or counter will be having only 0. It will not count when it is reset. If we come out of the reset, count will be equal to count plus 1. Means you need to understand in such a way that if this is my clock, okay, if this is my clock, I need to provide the reset first, and then I need to come out of the reset. Let's say this is your clock signal, and this is your reset signal. You need to provide the reset first, and then you need to make deassert the reset. This is reset assertion. You are asserting the reset, and this is your deassertion of your reset. You are coming out of the reset. From here onwards, your count starts. How it will count? Initially, it will be 0. From this clock onwards, this is your positive edge of the clock. It will count to 1. Then it will count to 2. So then, after that, you need to verify whether it will counting till the maximum value of count what it take. If it is a 2-bit counter, it will count only from 0 to 3. Correct? After 3, it should roll back to 0. Like that, we need to verify a simple count. You can observe here. Manually, if you provide values in a test bench in Verilog, let's say, yeah, this is for AND gate, not your counter what I have explained. This is AND gate. We will be writing y is equal to a ampersand b for AND gate functionality. Here we are providing manual values. Correct? This is how we will be writing a test bench in Verilog. But in system Verilog, we don't provide values like this. Everything should be randomized. Random values we need to provide for AB. And we need to drive it separately. Okay? I will show you. See here, this is your system Verilog architecture is. Okay, you will be not having a simple single module kind of code in system Verilog verification test bench. You will be having test bench top. Okay, then you will be having test. This is your test case. Suppose if you take a 2:1 mux, your test case would be 3 or 4 test cases. There are 4 test class you need to write. Then we will be having generator, we will be having driver, we will be having monitor, we will be having scoreboard. They are doing their own functionality. You will be not writing everything in a single code. In system Verilog, everything is systematic. Generator is one which will be generating the data. I said randomization will happen here. The data generation will happen here. Then this will provide to driver. This driver is a class. This will be knowing when actually I need to provide the data to DUT. Okay, if it is working with the clock, it should provide only in the positive edge of clock, right? That driver no. Similarly, let's take some complex example. Let's say this DUT is working with APB connectivity. We have APB protocol. That APB is used here as a bus. Then as per the APB protocol, we need to drive the things. We need to provide the input. Generator may generate any data, random data, but driver has to take care of when I am providing the data to DUT as per the protocol. That is your driver is. Then your DUT responds back. DUT will give your output. This we are talking about input here. This is your input. Okay, this is your inputs. These are all inputs. Then you will get an output, right? Who should read that output? There is a class called monitor. It is keep on monitoring your output coming from the DUT. Then there is another class called scoreboard. This gives you whether the test what you have performed on the design is correct or not. You will not verifying manually here by looking at the waveform. No. You will be looking at the waveform only when some test case really failing. You need to debug where actually the failure is. The very first thing you need to do is the print statements will be adding in the scoreboard. Scoreboard is a checker. It will check your functionality of a DUT and provide the test case is passed or test case is failed. If it is passed, no need to go and look at the waveform. Your waveform will be the last option for a verification engineer to debug. Okay. Before that, you should add many display statements in scoreboard. You will see those statements printed in your log, and you will verify whether your design is working as per the requirement or not. Okay, remember we are automated our test benches. We will be having checkers inside. So those checkers will be giving us the result that the functionality is passing or failing. Okay. It is not a manual verification. This is automated verification, let's say. Yeah, see here. This is a simple Verilog test bench to verify this adder. Okay, this is your adder. This is a class-based transaction we have written. And this module is a system Verilog test bench top. And see here, we have a display which will indicate, suppose if our DUT fail, it will indicate how many transactions what we generated for a DUT is passing and failing. So this intelligence we can add in a simple system Verilog module based test bench, and simple class added here. Okay, will give you many advantages, many automations, which will reduce the human effort in verification of functionalities of DUT through automated results. That's what I said. Different test case results. Then you will be having scoreboard to validate that result, whether it is correct or not. Then you will be having coverage analysis. It will give you the score that how many test cases you did perform and how many are covering the DUT. Okay. So this is exactly what design verification engineer is going to work on. Okay. This is a simple test bench architecture what I am showing here. Any simple test bench if you take in system Verilog will be having these many components. Not a single test bench we have. not a single module test bench how we see in Verilog we have. We will be having multiple components inside your test bench. Okay. So I think you guys got some surface level idea of how actually a verification engineer work and what are all the different aspects in verification. Okay. So if you have any queries, you can ask me.